that in our state experiment, what we proved? That magnetic field used when current is passed through any conductor. That conductor may be straight, that conductor may be circular, that conductor may be rectangular, whatever it is. So whenever current is passed through any coil or any wire, magnetic field is induced. And that we have already discussed in case of our state experiment. Now this is reverse of that. If magnetic field is induced due to electric field or due to current, then reverse should also be possible. Scientists started thinking regarding that why reverse is not possible. It should be possible because nature loves symmetry. So it's reverse, that is reverse of magnetic effect of current should be possible. And Faraday got the success in proving, yes, it is magnetic due to magnetic flux or change in magnetic flux or due to change in magnetic field, EMF is also induced. And that phenomena we call electromagnetic induction. So it is the phenomena in which an EMF is induced in a coil or conductor whenever there is change in magnetic flux linked to it. So whenever there is change in magnetic flux already we have discussed in the previous chapter. When we have discussed magnetic field, magnetic flux we have already discussed. So if there is anyhow, if we change this magnetic flux, EMF will be induced in that conductor or in the coil. This phenomena only we say electromagnetic induction. Induction of electric field due to change in magnetic flux or due to change in magnetic field. So the reverse of magnetic effect of current is possible. So what is this magnetic flux? This is the dot product of magnetic field intensity and area vector, B dot A. If this is uniform, if B is uniform, we can use this. If B is not uniform, then how will you find? Then this phi B will be B ds integration. For a small area we will find and then we will integrate it. It is given by the dot product of this only. Like work done. Dot product of force and displacement. If force is constant, then that formula will be applicable. If it is not constant, then other ways are also there. By integration or by plotting the graph. Already we are knowing. So, as this is given by the dot product of magnetic field intensity and area vector, that means it is scalar quantity. Already we have discussed it. So, what is the unit? SI unit of flux. IB we say magnetic flux is Weber. That's why the magnetic field unit is Weber per meter square. So Weber is the unit of magnetic flux. Just for understanding, we define magnetic flux linked to any surface as the total number of magnetic lines. In case of electric flux, already we have, in Gauss theorem, we have seen electric flux. Similar is magnetic flux. So just for understanding what we can say, magnetic flux linked to any surface. Always it will be linked to any surface. Is the total number of magnetic lines of forces crossing perpendicularly to that area. This already we have seen in previous chapter, and this is from here only we are getting this one. If magnetic lines of force is along the area vector, so if suppose this is the loop or any plate, and magnetic field is this one, uniform we are considering for the example. It may not be uniform also. Suppose this is B, area vector will be perpendicular to the loop. So this is the angle. So dot product of B and A. If loop is this one, suppose this is the loop, and magnetic lines of force is going this way. So in this case, theta is 0 degree. So flux will be maximum. This is the loop, and magnetic lines of force is this one, like this. So here area vector this one, magnetic field is one. So here theta is 90 degree. So flux will be 0. Here flux is maximum. And this flux will be B into A simply. Cos 0, 1. Okay, so this is already, just we have done all these things. Just revision, quick revision of this magnetic flux. Now, Faraday's experiment, how he proved this. Yes, an EMF is induced whenever there is change in magnetic flux. He performed so many experiments. The most common is by using this solenoid. Suppose the two end of this solenoid is connected by the galvanometer. So galvanometer will have the pointer, okay, like this it is. So this is the scale, this is 0. Both sides will have the divisions. So when there is no change in magnetic field, the galvanometer will show 0 deflection. Now, if a magnet is moved, either North Pole or South Pole, whatever it is, if a magnet is moved towards the solenoid, or solenoid is moved towards the magnet, when there will be relative motion between these two, magnet and coil, or solenoid. In place of solenoid, coil also may be placed. So when this magnet is moved, suppose it has come to this place. Here the magnetic lines of force which is coming from this way, suppose. So it will start crossing this coil. Magnetic lines of force is perpendicular to the loop, that is along the area vector only it will be, or opposite to the area vector, whatever you may consider. So angle between area vector and magnetic field is 0 degree. So there will be change in the magnetic flux linked to these loops, or magnetic flux linked to the solenoid. It will change. So what will we observe? So we will observe there is deflection in the galvanometer. It was observed whenever there is change in, means whenever there is relative motion between the magnet and the solenoid, a deflection was observed. Now when this magnet is brought here and left at this place only, the deflection will become 0. Why is it so? Or what does it mean? Though the magnetic flux linked to this solenoid is maximum, but then also there is no deflection in the galvanometer. So no EMF is induced. That means what? For EMF to be induced, there must be change in flux. When again it was returned, when it was pulled back, magnet, again it was observed there is deflection, but in opposite direction. If earlier it is showing right side deflection, then when it is moving back, it will show left side deflection. What will be the direction of deflection? That will come afterwards, or in class 10 we have seen. No, Lenz law we have seen in class 10 also. So what will be? So North Pole is approaching towards this, so it will oppose, Lenz law says, it will oppose the motion, or it will oppose the cause due to which it is induced. So North Pole will be induced. So when the magnet is moved this way, so North Pole will be this side. That means current will be this way. So deflection will be left, right side. When the magnet is moved away, we will observe the deflection is left side. So this simple experiment proves EMF is induced in the conductor or coil whenever there is change in magnetic flux linked to it. This we have already seen in class 10, so no, not in detail. Many experiments are there, or different cases are there. What will happen if North Pole is pointing or South Pole is coming this one, or South Pole is going away? Now this Faraday's law. So after observing so many, or after performing many experiments, he got the result that this induced EMF is directly proportional to rate of change of magnetic flux. That is, this E is directly proportional to d phi over dt. Phi is the total flux linked to the coil. If in the coil, what will be? If one loop is there, only one area of one loop will come. But in so many loops are there, then you have to consider total number of turns also. We will multiply it, area of each loop, and then multiply by the area. Sorry, number of turns. Then it will come total flux. Because in case of solenoid also, each loop is behaving like dipole. So the strength of magnetic field will keep on increasing. That we have already seen. So phi, this is phi what? Phi is total flux linked to the conductor or coil. So this for coil always we keep in mind. For coil, what is this total? This phi will be flux linked to each turn into number of turns. Or you can take total area as area of one loop into number of turns. So anyhow, whatever you, so this is always total flux. Now when we remove this velocity constant, we have to give a constant. This is we are giving a constant. Now this unit of flux is selected in such a way that the value of K is always 1. EMF already in unit was decided beforehand. Electromagnetic induction came afterwards. So unit of flux was selected in such a way that the value of K is always 1. That is, if changing the flux by 1 Weber in 1 second, if 1 volt EMF should be induced, naturally K value will become 1. So if flux is changed by 1 Weber in 1 second or 1 Weber per second, then EMF induced will be 1 volt. Flux is changed at the rate of 1 Weber per second. Then EMF induced must be 1 volt. That is the meaning of we are selecting the unit in Weber in such a way. And in order to induce EMF by 1 volt in 1 second, whatever flux change is taking place, that we will say it is Weber. Dimension of flux we have already, I think, seen. No.
So bottom part you don't love, sir.
So dimension, if you have not done, dimension of flux, unit V, that will be Weber, and dimension will be what? So this is what D5 means, B into A, and magnetic field intensity we are knowing 5, B into A. What was the
Sir,
what was the dimension of magnetic field intensity? You can apply this, you can find this. What will be the dimension of this one? I think dimension we have done, magnetic field intensity. So from there you can calculate yourself. Okay. Looks for this B is what? Always forgetting everything. Force per unit pole strength. Pole strength is ampere into length. That is B into area. So force will be what? MLT minus 2, that is the force, by AL. And area is L squared. That is the dimension. So what will you get? M L squared T minus 2. This is area, this is ampere, different. A minus 1. A is ampere, we can say. So this is not area. Current element is pole strength, ampere into length. Okay, so this way you can find the. Now the direction of this induced EMF. Or first we'll see, okay, direction of induced current is given by what are the two ways? The two in class 10 also we have seen. First is Faraday's right hand rule. And second is Lenz law. This we apply for this is applicable to straight conductor only. If it is a rectangular coil, then also we can apply for all four are in different way. So for straight conductor only we can apply. The second one is Lenz law. This is applicable to all. Whatever whatever the shape of the conductor may be, whatever the shape of the coil may be, no problem. This Lenz law is applicable. That can be in straight wire also, we can apply Lenz law. So the most common one is the Lenz law, and frequently we use this one. Right hand rule says if we stretch our 3 fingers perpendicular to each other, just reverse of left hand rule. Left hand rule gives direction of force, in which direction force will be experienced by the current carrying conductor when placed in magnetic field, whereas this right hand gives the direction of induced current. So this is in the direction of magnetic field. The thumb will be in the direction of motion of the conductor. Then the middle finger will give the direction of induced current. So here what will be the thumb of right hand along motion of the conductor. Forefinger of right hand along magnetic field. Then middle finger will give the direction of induced current. So this is Faraday's right hand rule. Right hand thumb rule gives the direction of magnetic field when current is passing through a straight wire. That was right hand thumb rule. Fleming's left hand rule gives, it is Fleming's, not Faraday, sorry. Fleming's left hand rule will give direction of magnetic field, whereas this right hand rule of Fleming gives direction of induced current. Fleming's right hand rule. Okay. So according to this, thumb we have to keep in the direction of motion of the conductor. Now we'll see some example then only.
So shift the camera little downwards, sir.
Now suppose we are having the magnetic field cross. And there is one conductor which is moved in this direction. Then you will be asked what will be the direction of induced EMF, or what will be the direction of induced current. Mainly we will find the current direction. Okay, so if we apply this right hand thumb rule, what will be? No, Fleming's right hand rule. So this will be in the direction of magnetic field. So this is the direction of motion of the conductor. Thumb will be in the direction of motion. So it is moving upward. Then this middle finger will give the direction of current. That is this one. So if the circuit is closed, then only current will pass. If the circuit is not closed, current will not pass, but EMF will be induced. So if circuit is closed, just to imagine, if the circuit is closed, what will be? If the circuit is closed, suppose here around resistance is there, circuit is closed, then current will pass in this direction. So in this circuit, current will pass this way. If circuit is not closed, then this will behave as the source of the current. Means EMF will be induced. Now what will be the direction of EMF? As the current is passing through this, so it will behave as source. Which source? When we are taking this one like this and connecting this way, this is the circuit, what will be? It will give the current in this direction only. That means if circuit is not complete, here slowly positive charge will start accumulating, and here negative charge will start accumulating. That means here this side potential will be higher, this side potential will be lower. How much potential difference? That we will derive afterwards. So this rod will start behaving as source, same as the dry cell or any cell we can say, or solar cell. So this terminal will coming at higher potential and this will be lower potential. And if circuit is complete, then current will flow. If circuit is not complete, then also EMF will be induced. So direction of current or direction of induced EMF, whatever it is asked, meaning is same. So if the circuit is complete, current will be according along the middle finger. If current is not there, if the circuit is not complete, you imagine that current is passing in this way according to this rule. That means this one will be positive, this one will be negative, not this one positive. Don't be confused. This will become the source. So when you complete the circuit, what will be the direction of current? Accordingly, you see what will be positive and what will be negative. Now, suppose this is magnetic field. And there is a conductor which is moving in the same direction. How much EMF will be induced? So in this way, there is no change in the flux. So in this case, EMF induced will become 0 because 3 fingers should be perpendicular. Then only we can apply. So both are in same direction. B and V are in same direction. So here EMF induced will be 0. No current will pass. But once in the same case, suppose this is the magnetic field and conductor is moving this way. Then what will come? In this case also, no change in the flux. No line is crossing. No, flux is what? Number of electric lines of force crossing perpendicularly. So if you are moving, suppose we are coming to this place, that means this is the area vector. But V is in the same direction of magnetic field. So V and B will be in same direction. Okay, so this one will come afterwards. Now next is Lenz law, which is the important one. So Lenz law says according to this law, it is said the EMF will be induced in the conductor or the coil in such a way that it can oppose the cause due to which it is induced. So according to this, the EMF is induced in the conductor or coil in such a way that it can oppose the cause due to which it is induced. What does it mean? So come to the same experiment what we have done previous one. Suppose there is a solenoid so a galvanometer is connected between these two, and here what was that? This magnet was moved. Now when magnet starts moving towards the solenoid, the flux start increasing. There is change in flux. If magnet comes here and is stationary, no EMF will be induced because there is no change in the flux. So when magnet starts moving towards this solenoid, the flux linked to this solenoid increases. Now EMF will be induced. Now EMF will induce in such a way that it can oppose the cause. And what is the cause here? EMF is induced due to motion of the magnet. So it will oppose this motion. How will it oppose? By repelling. It is moving towards the magnet, towards the solenoid. Due to that only it is induced. So it will oppose by repelling it. And to repel, what will be? North pole must be present here. South pole will be here. For north pole to induce here, what will be? The current will become anti-clockwise. So this will be the direction of current here. When magnet is moved towards the solenoid, naturally the deflection of galvanometer will be this side. When the magnet is moved away, what will be?
So
When the magnet is moved away, it will again oppose. How will oppose? By attracting it. And to attract, opposite pole is induced. So when magnet starts moving away, here south pole will be induced. Naturally, deflection of galvanometer will be this side. So if you keep on moving this magnet here and there, like this left and right side, what will be? You will get the deflection sometime left, sometime right, sometime left, like that. When you are approaching, your magnet is approaching this side, deflection left. You keep it here, no deflection. Move it back, left deflection. So this way, this deflection will continue till there is relative motion. So whenever there is, now take another example. Suppose this is the uniform magnetic field. we are moving this loop, closed loop is there. We are moving this closed loop through this magnetic field. What will you observe when this loop is going to enter into the magnetic field? Its flux will increase. When the loop is here, after some time the loop has come to this place. So naturally the flux is increasing. Which flux? Inward. Magnetic field is increasing. When there is change in flux, EMF is induced. Now, according to Lenz law, this EMF will induced in such a way that it can oppose the cause. And what is the cause here? The flux is increasing here. Inward flux is increasing or inward magnetic field is increasing. So the current will pass in such a way or produce in such a way that it can decrease this magnetic field. To decrease the magnetic field, the induced magnetic field must be outward. And for outward magnetic field, what will be the direction of current? Anticlockwise. So when the loop starts moving into this magnetic field, the current will be anticlockwise. What will happen once the loop is completely inside? Here current will become zero. No current will pass because there is no change in flux. Once the loop is completely inside the magnet, no change in flux. Now, when this loop starts going out, now what will happen? The flux is decreasing. So it will try to maintain the flux. It will oppose. How it will oppose? By maintaining the same amount of flux. So it will try to maintain the flux. That is, the magnetic field will be induced in the same direction. That is inward. Inward means south pole. So south pole will be induced now, or this loop will behave as south pole. So what is the direction of current? Clockwise. So when the loop is going inside, anti-clockwise current was there. Completely inside, no change, no current. Loop starts going out, current will be clockwise. So this is how we will find the direction by using Lenz law. Always you keep in mind. So if magnetic flux is increasing, EMF will be induced in such a way that it can decrease the magnetic flux. If magnetic flux is decreasing, the EMF will be induced or current will be induced in such a way that it can increase the magnetic flux. Now, if we apply this law, according to this we got, the magnitude of EMF induced is the rate of change of magnetic flux, d phi by dt. This we have got, previous one. Earlier one, Faraday didn't give anything about the direction. Direction was given afterwards. The Fleming and then Lenz give the direction. So according to both, whether it is you apply the Fleming's or this Lenz law, you will observe that EMF is induced in such a way that it can oppose the cause. So when phi is increasing, this induced EMF will try to decrease the flux. If phi is decreasing, EMF will induce in such a way that it can increase the flux. That means this E will be always given by minus d phi by dt. If phi increases, induced EMF will try to decrease. And vice versa. If phi decreases, then this induced EMF will try to increase. So this is the general formula for induced EMF. The magnitude and direction both. So always we have to keep in mind, the direction of EMF we have to decide by using Lenz law. Okay.